A piece of iron is dropped from an aeroplane from a height of 1.2 kilometers. If 75% of the kinetic energy of the iron is converted to thermal energy on impact to the ground, determine the rise in temperature. Okay, we're going to need the specific heat capacity of iron, and it can be found in the book, I think, if I can just get that value. We have iron is 4.7 times 10 to the 2. It's 470 joules per kilogram per Kelvin. So we've got that amount we're going to need. Now the kinetic energy obviously is equal to EK is equal to a half mv squared, and that is going to equal to the height that it was dropped. So we're going to have mgh. So the kinetic energy is going to equal that, which is equal to the mgh. Now this is equal to mass. Let's use 10 for gravity, and our height is 1,200 meters. Put that into meters. So we're going to get our energy, kinetic energy is going to equal that joules. We're going to get 12,000 m. We're not actually given the mass, but probably we'll find the mass will actually cancel out. So it's 12,000 times the mass. Now 75% is converted, so the heat that we get is actually equal to 0.75 times by the 12,000 m, and that equals to we're looking at the determine the rise in temperature. Well, that will equal m times the C, which is this one over here, times 470 times the change in temperature that we're trying to work out. Now you'll notice here that the masses cancel out nice and conveniently, and so I just divide both sides by 470 on both sides, 470, and I'll get my change in temperature. So I'm going to get brackets 0.75 times by 12,000. That's a pretty easy number to work out, but anyway, I'll just do it in the calculator, and divide it by 470, and we get 19.14. Now we work into two significant figures here, so our change in temperature is going to be 19 Kelvin, or degrees Celsius would be fine. That will give us our change in temperature. Alright, so we've got our last two questions here. A heating fluid releases 4.2 times 10 to the 7 joules per kilogram of heat as it undergoes combustion. If the fluid is used to heat 250 decimeters cubed of water from 15 degrees to 71 degrees, and the conversion is 65% efficient, determine the mass of heating fluid that will be consumed in the process. So let's firstly work out the heat that is required to do that, and then we can from that work out the amount of energy that would have to be supplied, and from that the amount of heating fluid. So let's firstly work out the heat required to heat that amount of water. Now again, it's 250 decimeters cubed. That would be the same as 250 kilograms. So we're going to get 250 times by C, which is 4,200, and our temperature change is from 15 to 71. So there we're going to get 56. Is that correct? Please always just check my numbers. I'm quite liable to make a mistake here. So we're going to get 250 times by 4200 times by 56. So we get 58.8 times 10 to the 6 joules. Now, the amount of energy, therefore, that would be our basically our output energy. This would be the actual useful energy. Now, we have it at 65% efficient. So the energy that we put in, let's just put this over here of out. The energy that in times 0.65 equaled, 0.65 would equal this 58.8 times 10 to the 6 joules, because it was a 65% efficiency. So with the energy that was actually supplied, or the energy that was from the heating fluid, is actually to 558.8 times 10 to the 6 joules divided by 0.65. So I'm going to divide this by 0.65, and I get this value over here. It's going to be 990.5 times 10 to the 6 joules. Alright, so we've got that. That's the total energy that actually comes by means of the heating fluid. Now, for every kilogram, the number of kilograms that we're wanting to use, the mass, another easier way would obviously be to just say mass, would equal this 90.5 times 10 to the 6 joules divided by this 4.2 times 10 to the 7 joules per kilogram. So as you can see, our joules will cancel, our kilogram will go to the top and it'll become kilograms. So we just divide this value by 4.2 exponent 7, and we get that it is 2.2 kilograms would be required. Alright, so I hope that makes sense. And then finally, this final one, I'm going to just need to erase some of this so that I can have some space here. Hope you got all of that. Back to here. Alright, so we have a large boulder of 125 kilograms falls off a cliff of a height of 122 meters into a pool of water containing 120 kilograms of water. Determine the rise in temperature of the water. Assume that no water is lost in the entry of the boulder and all the heat goes to the water. So basically what's going to happen is that this boulder is going to fall down 122 meters. It's going to have a certain kinetic energy at the base, which we can write as a half mv squared, which can be calculated from your mgh, because the potential energy at the start. So the energy that we'll have due to kinetic energy would equal 125 times by 10 times by 122. So we can just calculate that out. 125 times by 10 times by 122, and we get 152,500 joules. Now, all this energy is said to, all the energy goes to the water. So as it falls into the water, obviously the water would cause it to deaccelerate, it will do work. That work will be in the form of friction. It will cause the water to rise. So this, using Q is equal to MC change in T, we've got this is the input energy 152,500 The mass of the water is 120. The C of water, specific heat capacity, is 4,200. Change of temperature. So we're just going to divide this 1522, we're going to divide that by 120 times by 4,200. Just remember to put that in brackets, and we get it's going to be a rise of about 0.302. I did that because we seem to have three significant figures here, and that would be Kelvin or centigrade would also be fine. Okay, so there we have exercise 3.3. Thank you very much.